Well, tonight's webinar on alternators, it's a little bit more material than what we've had the last couple of times, so I'm going to try to go through it as quickly as I can so that we have time for questions. Lots of stuff to discuss about alternators and charging systems and troubleshooting charging system problems and so on. So let's start. And we'll start with just the very basics of how alternators are constructed. Conceptually, an alternator is a very, very simple device. It consists of a rotating magnet inside a stationary coil of wire. And as you rotate the magnet and rotate the magnetic field associated with that magnet, it induces an alternating current in the coil. We call the rotating magnet the rotor, and we call the stationary coil the stator. And those are the two primary components of the alternator, along with the third component we'll get to in just a moment, called the rectifier assembly. Because our aircraft are set up to use direct current instead of alternating current, the alternating current from the stator and the alternator is passed through a rectifier assembly, which is a full wave rectifier bridge that converts the AC to DC so that we get DC out of the alternator. Now what we get out of the alternator is not exactly DC. It's rectified AC, and so it's DC with a lot of bumps in it. And if we simply did this and rectified single-phase AC with a full-wave bridge, the output of the alternator would have an awful lot of noise in it, and although it would probably charge our batteries okay, it would probably make all sorts of noise in our avionics and so on. So we're going to have to figure out a way to solve that. We'll get to that in a moment. But at any rate, the alternator has three principal parts. It's got a rotor, which is a rotating magnet. It's driven by the shaft that sticks out of the alternator and is typically driven by the engine. There's a stator, which is a big coil of heavy wire in which the alternating current that the alternator generates is induced. And then there's a rectifier assembly consisting of silicon diodes to convert that AC into DC. Now, as I said, it's not quite that simple because we have two problems with this very simple alternator that we've just postulated. One is that the DC that would come out of the alternator would have an awful lot of ripple on it, and as I said, it probably charged the battery fine, but it would probably also raise hell with our avionics and create all sorts of noises in our noise canceling headsets and so on. So we're going to have to do something to smooth out that pulsating DC into something a lot closer to pure DC. The second problem is that we need to regulate the output voltage. If we simply had a permanent magnet rotor, then the voltage that it induced into the stator as we rotate the alternator would vary with rotor RPM. So the faster we turn the alternator, the more voltage it would generate. And that doesn't work real well with our aircraft because we want a constant output voltage. And since the alternators are engine driven, and since the RPM of the engine changes quite a bit, it just wouldn't work real well. So we're going to have to find some way to regulate the voltage output of the alternator and keep it more or less constant. So let's see how we solve those two problems. The first problem, getting rid of the ripple, the way that's solved in aircraft alternators is by making the rotor not a simple coil of wire, but a more complicated coil of wire with three different windings. And there are a couple of ways to do that, but the way it's done in almost all aircraft alternators is by winding the rotor in a Y configuration, as illustrated by this schematic in the lower right-hand corner, where there are basically three windings that join at a common point in the center. And the three windings when you rotate a magnet inside of them, produces three-phase AC instead of single-phase AC. In order to rectify the three-phase AC, we need a little bit more complicated rectifier assembly. We need to use 6 silicon diodes instead of just 4. But the result of rectifying three-phase AC is to produce an output that is much closer to pure DC. Again, this is the way the rectifier assembly works when we have three-phase AC. It requires 6 diodes. And here's what the output looks like when we rectify those 3 phases. There's still a little bit of ripple on it, but it's not very much. And the output is much closer to a pure DC waveform than if we were rectifying single-phase AC with a simple single winding in the rotor. Here's another picture of that, whereas the orange line is what we would get out of the alternator if it was a single-phase alternator, and the reddish line shows what the output looks like with a three-phase winding, which is the way virtually all aircraft alternators are set up. Here's an oscilloscope trace of what we get out of an aircraft alternator, and you can see there is a little bit of ripple on it, but the ripple is very small, typically less than 0.2 of a volt. Not enough to do much mischief, not enough to create much of a whine in our headsets or to cause our avionics to get upset. Here's an actual photograph of an alternator rotor, showing the way the 3 different windings are interleaved when it's constructed. It's actually a fairly complicated set of windings, but if you were to lay it all out flat, what you'd find is that it was 3 separate windings all interleaved, producing a three-phase AC. So that's what the rotor actually looks like inside an aircraft alternator. Now the second problem we have is regulating the output voltage, so that the alternator will put out a pretty constant voltage even when we change the RPM that we turn the rotor at. And the way we accomplish that is to have the rotor not be a permanent magnet, but to be an electromagnet. And we can vary the amount of field current that goes through the rotor, and therefore vary the intensity of the magnetic field. And by varying the intensity of the magnetic field, we can vary the voltage that comes out of the alternator. The output voltage is a function of 2 variables. One is how fast we turn the rotor, and the other is how much field current we put in. So we set up a regulator that senses the output voltage of the alternator, and if the output voltage is getting a little high, it reduces the amount of field current and weakens the magnetic field of the rotor to compensate. And conversely, if the output voltage is getting a little low, maybe because we reduced RPM a little bit, say gone from climb to cruise, it will increase the amount of current, field current that goes through the rotor, increase the strength of the magnetic field, and bring the output voltage back up. So the regulator is basically sitting there watching the output voltage of the alternator and constantly making corrections in terms of how much field current we supply to the rotor in order to hold the alternator output voltage constant. It's pretty simple. Here is how the rotor of an actual aircraft alternator is constructed. It's an electromagnet, so it has a coil, and it has a pair of pole pieces with sort of interlocking fingers, so that there's north poles and south poles that interleave with one another. And because this thing is rotating and we have to supply field current to that coil, we do that with a set of slip rings on one end of the shaft. Typically it's the end of the shaft, the opposite end of the shaft from the one that sticks out of the alternator and is driven by the engine, so it's what we call the non-drive end of the shaft. And so there are slip rings on one end of the shaft, and there's a brush assembly with some spring-loaded carbon brushes that ride on those slip rings. And so we supply the field current to this rotating rotor through the brushes and the slip rings to energize the coil in the rotor and to create the rotating magnetic field that energizes the stator and creates the output of the alternator output. Here's what a rectifier assembly looks like, and there are actually lots of different configurations of rectifier assemblies, but what you'll find that they all have in common in aircraft alternators is that they all have 6 silicon diodes arranged in a 3-phase bridge, as we saw in the earlier diagram. Sometimes the diodes are visible from the outside of the alternator. Most of the time they're not visible. But there are always 6 diodes, and they're all mounted on a big plate that acts as a heat sink. And that's basically what the rectifier assembly in the alternator looks like. Here's a picture inside of an aircraft alternator with the rotor removed, and you can see the stator windings out at the outer edge of the photograph. And you can see the diodes that represent the rectifier assembly. And you can see the brush assembly with the 2 brushes that are just sort of dangling out there. And on one of them you can see the little spring behind it. The brushes are spring-loaded so that they press against the slip rings on the non-drive end of the rotor shaft, which has been removed from the alternator to take this photograph. So those are the basic components of this thing. Here is a rotor mounted to the non-drive end cap of an alternator. You can see the slip rings on the bottom there, and you can also see a fan that's mounted on the opposite end of the shaft. Most alternators have some sort of a fan, either external or internal to the alternator, that blows cooling air over the silicon diodes in the rectifier assembly, because like most high power solid state things, those rectifiers put out quite a lot of heat, and they need to get cooling air. The voltage regulator, which again is a device that watches the output voltage of the alternator and adjusts the field current to hold that output voltage constant. The regulator can be mounted either inside of the alternator or externally as a separate component. In most modern automobile alternators, the regulator is built right into the alternator. It's just a few little solid-state chips that fit right inside the alternator. In all of the certificated aircraft alternators with which I'm familiar, the regulator is external to the alternator. It's a separate part that frequently is mounted on the firewall or something fairly close to the alternator. My airplane, which is a twin, has the regulators actually mounted in the cockpit underneath the co-pilot seat. But in all of the certificated aircraft alternators with which I'm familiar, the regulator is an external device, not built into the alternator, although it is built into the alternator on a lot of car alternators. And I suspect that there are a lot of home builds that are using automotive alternators with internal regulators. But on certificated aircraft, they're a separate box. Sometimes the regulator is called by a different name. It may be called an alternator control unit. It may be called a field control module. But regardless of what it's called, it basically does the same thing. It watches the output voltage of the alternator and varies the field current to try to hold that output voltage constant. It's a pretty simple device. Most aircraft systems, and I think all certificated aircraft systems, have overvoltage protection That is, if the regulator was to fail, in certain failure modes, the alternator could produce, particularly at high RPM, could produce such a high output voltage that it could start frying expensive components. And so the system typically has some sort of overvoltage protection that kicks in if the regulator fails and lets the alternator put out a damagingly high output voltage. There are two basic systems for providing overvoltage protection. One is called an overvoltage relay, whose function is to basically open the field circuit if it senses excessive voltage, and essentially eliminate the magnetic field from the rotor and shut the alternator down that way. A second approach that is used in certain charging systems is called a crowbar circuit. The crowbar circuit, rather than opening the field circuit, shorts it to ground and causes its protective device, which is typically a circuit breaker, possibly a fuse, to open and to disable the system that way. But either way, the overvoltage protection normally will shut down the charging system quite rapidly. In most systems, there's some sort of a warning light that will come on that tells you that the system is shut down and that you're operating on battery power only. And then normally there's some way to reset it from the cockpit, often by cycling the alternator field switch off and then back on or something like that. In the case of a crowbar circuit, it would be reset by resetting the circuit breaker, the field circuit breaker that was popped. There are several series of alternators commonly found on certificated aircraft, and since most of them are derived from automotive alternators originally, they're often called by automotive names. The left three photos show what's called a Ford series alternators that are commonly found on Cessna single engine aircraft. Now again, don't be misled, they're not manufactured by Ford. Most of them nowadays are manufactured by what used to be Kelly Aerospace and is now Hartzell Engine Technologies. But they're based on, originally based on Ford automotive alternator design that was modified for aircraft use. The center picture shows a Chrysler series alternator that's recognizable by all those cooling slots, and is commonly found on Piper Singles that are powered by Lycoming engines. And the alternators on the right side are what are known as the Prestolite series, and these are mostly gear-driven alternators and are often found on Bonanzas and Barons and twin Cessnas, Cirruses, Columbias, aircraft like that with Continental pearl mold case engines that accommodate a gear-driven alternator. Here are a couple of typical alternator installations on Lycoming engines. Most commonly, they're front-mounted, and they are belt-driven off of a big pulley that is behind the starter ring gear. The one problem with this arrangement, which is very commonly found on Lycoming engines, is that in order to change the alternator belt, you have to pull the prop, which is a little inconvenient. So mechanics will often use a trick that when they do change the belt, they'll put another belt in place and kind of tie wrap it out of the way, so that if the first belt needs to be changed, you can cut it off with a pair of dikes, and then thread the second belt in place that was placed there earlier without having to remove the prop. But except for the fact that it's kind of inconvenient to have to pull the prop in order to change the alternator belt, is a pretty good setup. This picture shows some alternator installations on TCM Sandcast series engines, as are found in most Continental powered Cessna single engine airplanes, 182s, 210s, 206s, that sort of thing. The alternator is mounted behind the engine in the accessory case, and it's driven by a belt that is frequently driven off of a drive pulley on the back of the engine starter adapter. There are a number of different arrangements there, but these are some typical installations on Cessna Singles. The big problem with these is the fact that the alternator being mounted behind the engine in the accessory area is in a pretty hot area. There's not a lot of cool air compared to, say, the Lycoming installation, where the alternator is up front, right in the with a lot of cold air coming into the front of the cowling. So with these rear-mounted alternators, we frequently run into heat-related problems, premature failures caused by rectifier diodes blowing out because they're not being cooled well enough. And it's often necessary to arrange some sort of a blast tube to blow cold air on the alternator when it's mounted in this position. Here is the lower left image is a typical press-to-light series alternator installation on a per-mold case Continental engine, as you might find in a twin Cessna or a Bonanza or a Cirrus or a Columbia, where the alternator is mounted to the front left, at the front right side of the engine case, and is actually driven right off of a big face gear inside the engine that's mounted on the crankshaft. We'll see a picture of that shortly. The lower right picture is a picture of a dual alternator installation, I believe off of a Columbia, where the primary alternator is gear driven and mounted to the front right side of the engine, and the number 2 alternator is mounted on the opposite side of the front of the engine and is driven off of a pulley behind the propeller, quite similar to the way it's done on Lycomings, except that in this case the alternator is mounted up high rather than down low. But this is a dual alternator installation. I believe it's on a this one was on a Columbia with a gear-driven number 1 alternator, a press-to-light series, and a belt-driven number 2 alternator. Here's a photo of a Continental engine, like with one of the gear-driven alternators, like we saw in the previous photograph. Might have been off a Bonanza or something, or a Cirrus, with the alternator actually removed, and you can look in the big hole where the alternator mounts, the hole in the side of the crankshaft or the side of the crankcase, and see the big face gear that is mounted to the crankshaft. That face gear or ring gear mates with an elastomeric drive hub that mounts on the alternator shaft. And the purpose of that elastomeric drive hub is twofold. One is it acts as a shock absorber to insulate the alternator from the power pulses of the engine, because of course the engine turns that ring gear and the propeller and so on with a lot of fairly sharp power pulses, and the elastomer and the elastomeric drive hub tends to absorb some of those shocks, prevent them from being transferred to the alternator. The second and the most important function of the drive hub, of the elastomeric drive hub, is to disengage in case the alternator were to seize up for some reason. Say one of the bearings in the alternator went bad, and the shaft seized. You wouldn't want that to take out the engine. So the elastomeric hub is designed to disengage if the torque on it becomes too high. The elastomer is attached to that little gear that is driven off of the ring gear, and it's mounted in a cup which is keyed to the alternator shaft, and the elastomer is kind of glued into that cup with some kind of super glue, which is designed to shear if the torque is too great and disengage the alternator from the drive gear in order to protect the engine in case something bad happens to the alternator. There's a fourth kind of alternator I'll just illustrate here. This is a backup alternator built by B&C Specialty Products that we see installed as a number 2 alternator frequently on Bonanzas and on many Cirrus aircraft. It's designed to mount on an accessory pad where the vacuum pump would normally mount, except that in aircraft that use these backup alternators, typically they're all electric airplanes that don't have a vacuum pump, and so this little B&C backup alternator, standby alternator, mounts right on the accessory pad where the vacuum pump would normally mount, and is driven off that pad. And very much like a vacuum pump, it has a frangible plastic coupling that will shear if something bad happens to the alternator, and it shears in order to protect the drive gears in the engine in case something bad happens to the alternator. Let's talk a little bit about common failure modes of alternators. There are both internal failures and external failures. Internal failures include failures of the stator winding, either opens or shorts, often caused by vibration or excessive heat. There are a bunch of crimp and solder joints in the rotor winding that can be compromised if the alternator has excessive vibration. There are also failures of brushes and slip rings. The brushes obviously have a finite life and they wear out after a while. And as they wear, frequently they'll start making intermittent contact with the slip rings and cause the alternator to fail in an intermittent fashion. We see a lot of failures of rectifier diodes, either opens or shorts, most commonly because the alternator is not receiving enough cooling air, and the diodes wind up heating up and failing, just like any high-power solid-state device will do. They put out a lot of heat, and they need to have plenty of cooling air to keep them from getting too hot. And we also see problems with the bearings in the alternator failing. There are 2 bearings in every alternator, one on the drive end, one on the non-drive end. Obviously, if the bearings start to fail, there'll be problems. If it's a gear-driven alternator, the hub will probably shear. If it's a belt-driven alternator, it'll start causing the belt to slip and so on. External failures are either something that prevents the alternator rotor from actually turning. If it's a belt-driven alternator, maybe the drive belt is slipping, or it's broken, or it got thrown off the pulley. If it's a gear-driven alternator, the drive coupling may be slipping or sheared. The other kind of external failure is that the alternator is not receiving field current. And that can be caused by either the regulator itself failing, or the overvoltage relay opening up, or something going wrong with the field switch or the field breaker or fuse, or very commonly a problem with the wiring, where the wiring has been chafed or a connector is not making proper contact anymore, that sort of thing. But obviously anything that prevents the proper supply of field current from the regulator to the alternator is going to cause the alternator to stop putting out voltage. Here's an uncommon failure mode. This was a pretty dramatic picture. This was a gear-driven alternator on a per-mold case Continental engine, where the alternator shaft actually snapped, and liberated the drive hub, and it just started bouncing around inside the engine, doing all sorts of damage. This is a pretty bad failure. After something like this, you'd have to tear down the engine because there's all sorts of metal and stuff in there, and all sorts of damage to the crankcase, not to mention the drive hub and so on. This is a very uncommon thing. I've only ever seen this happen once or twice. Not sure exactly what caused the shaft to break, but I suspect that it was one of two things. Either the alternator was not mounted properly and there was excessive side load on the shaft, or it could possibly have been an old series Prestolite alternator that had a known problematic non-drive end bearing that had a tendency to seize up. If the bearing seized, theoretically the hub should have disengaged rather than having the shaft break, but apparently that didn't happen in this case. So my guess is that this was a problem caused by misalignment of the alternator when it was installed on the engine, but it's hard to be sure. Pretty uncommon situation. Charging system circuits. Here is a charging system circuit out of a typical Piper single and one out of a typical Cessna single. And if you look at them carefully, you'll find that there isn't a whole lot of difference between them, with the exception of the meter. The Pipers use a load meter, which is an ammeter that shows how much current the alternator is putting out, and it's got 0 on the left side of it. Cessnas typically use what's called a battery ammeter, which shows the amount of current going into or coming out of the battery, and it's typically a zero center ammeter, where 0 is in the center of the scale, and it can deflect either to the right to show that the battery is being charged, or to the left showing it's discharged. Other than the location of the meter and the way that the meter scale is calibrated, both of these systems are pretty much the same. And this is the Cessna one, or sort of a simplified version of the Cessna one, but let's just kind of go through its primary features. Obviously, we start with an alternator, a regulator, an overvoltage relay. In this case, the overvoltage relay is a separate device which shuts down the power to the regulator if it senses that the bus voltage is too high. But in some systems, it's combined into the regulator, into the same box, in which case the regulator may be called an alternator control unit rather than a regulator, because it's got the overvoltage relay built right into it. There's a field switch that where the pilot can energize or de-energize the alternator field circuit. In a lot of Cessnas, the field switch is combined with the battery master switch into a split master switch on the panel, but it's really two separate switches, an alternator side and a battery side. There's a field circuit breaker that provides protection to the field circuit. In some aircraft, that's a fuse rather than a circuit breaker. Then there's the big circuit breaker that provides circuit protection to the alternator output lead, the big heavy wire that goes from the alternator output to the main bus. As I indicated, in some aircraft, the regulator and overvoltage relay will be combined into a single box that will often be called an alternator control unit or field control module, but it's just a regulator with overvoltage protection built in rather than being separate. So how do we troubleshoot a system like this if it stops charging? There's a pretty logical procedure that you go through, and I'll just quickly kind of outline it to you. First thing we want to do is make sure that the alternator rotor is actually turning. It takes two things to make an alternator work. We have to turn the rotor, and we have to provide field current to energize the rotor and create a magnetic field. So the first thing we want to do is make sure the rotor is actually turning. That's real easy if it's belt driven. We just pop the cowling and turn the prop and see if the rotor, see if the alternator turns. If it's a gear driven alternator, it's a little harder because the drive is normally concealed. but typically we can shine a flashlight through the cooling slots in the alternator, and then turn the prop by hand and look through those slots, and we should see the rotor turning. If the rotor isn't turning when we turn the prop, we know we got a problem. The hub is probably sheared or something. And if the alternator isn't turning, then we can't really expect it to be putting anything out. Assuming that the rotor is turning, the next thing we want to do is get out a meter and make sure that the alternator is getting field voltage. If the alternator is turning and it is getting field voltage, and it's not putting anything out, then we're done. It's the alternator's fault. Now, we could troubleshoot further and figure out why the alternator isn't working. Maybe a diode's opened up. Maybe the rotor coil has a problem. Maybe the brushes or slip rings have a problem. But typically, we don't really have to troubleshoot to that level, because if the alternator isn't working, we're going to have to pull it off the engine and either send it out to be repaired or order an exchange replacement and install it. And it really doesn't matter exactly why the alternator isn't working. If it's not working, that's pretty much all we need to know, because we know we need to replace it. But a lot of charging system failures are not the alternator's fault, so we don't want to pull alternators off an airplane unless we're really sure it's the alternator's fault. If there is no field voltage getting to the alternator, then the problem is outside the alternator, so we're going to have to continue. So the next thing we want to do is find out whether the regulator is furnishing field voltage. So we put our meter on the field terminal of the regulator. If the regulator is furnishing field voltage, but we're not seeing it at the alternator's field terminal, then we obviously have a broken wire or a bad connector or something. If the regulator is not putting out field voltage, then we need to see whether the regulator is getting power in. If it's getting power in but not putting field voltage out, then the regulator is bad, and we're going to have to replace it. But if we're not getting power into the regulator, then we need to keep going backwards and find out where the power is being lost. Maybe the overvoltage relay is bad. Maybe the alternator switch is bad, or the wire between the alternator switch and the overvoltage relay is bad, and so on. We just keep going back with our meter until we find out where the power is getting lost, and we've found out which component is bad. It could even be the protective device, the circuit breaker, or the fuse. Again, first step is to make sure the alternator is turning. If it's not turning, we need to figure out why. It's a mechanical problem. The belt is slipping, the drive hub is sheared, something is preventing the alternator from turning. Second step is to see if there's field voltage at the alternator. With the engine not running and the system powered up, we should be seeing something something close to battery voltage, 12 or 24 volts, at the alternator field terminal. If we don't, the problem is not the alternator, it's something in the field circuit. If we are seeing voltage at the alternator field terminal and we are seeing that the rotor is turning, then we know we have a bad alternator and we're done. And if it's outside the alternator, we have to keep tracing back with our meter until we find where the problem is. Might be the regulator, might be the wiring, might be overvoltage relay or alternator field switch or circuit breaker, whatever, but it shouldn't take very long to figure out what the culprit is. Frequently, we can bench check an alternator by measuring the resistance across the field. If it's a 12-volt alternator, it ought to be somewhere in the order of 3 to 6 ohms, and if it's a 24-volt alternator, it should be something on the order of 10 to 18 ohms. And if we turn the alternator shaft, the field resistance shouldn't jump around a bunch. If it's jumping around, then we know that there's a problem with the brushes and slip rings, and that's probably what our issue is. Again, I think we've gone through all of this, how we would trace with a meter to figure out what the problem is. It shouldn't take more than a half an hour, maybe 45 minutes at tops to troubleshoot a charging system problem. And if your mechanic can't figure out what's wrong with your charging system definitively in 30 to 45 minutes, he's probably not the right guy for the job. I have noticed that a lot of A&P mechanics are a lot less comfortable with electrons than they are with mechanical things, and sometimes problems with a charging system are best taken to an avionics shop because avionics techs are comfortable with electrons and comfortable using meters and that sort of thing, and that's really what we need to do to troubleshoot them. I'll probably skip over this stuff. It gets a little bit technical, but we can use an ohmmeter to check the rectifier diodes and to make sure that they're conducting in one direction, not in the other direction. But again, if we decide that we've got good field voltage at the alternator field terminal and that the alternator rotor is turning and yet it's not putting out voltage, we're pretty sure the alternator is bad, and we probably don't have to go much further in our troubleshooting. We just need to pull the alternator off and get it repaired or replaced. I'll just skip over this stuff. Now, if we decide the alternator itself is at fault, we've got basically three options. You can replace it with a new one, you can replace it with a rebuilt unit or a repaired unit, exchange unit, or you can send yours out for overhaul. My preference is not to replace alternators with new ones because most of the new and rebuilt alternators these days come from Hartzell Engine Technologies, which is the new name for Kelly Aerospace. Hartzell bought out Kelly's interest in all his alternators, and those guys have some pretty serious quality control issues, and we see a lot of infant mortality failures with new and rebuilt alternators that come from HET. So for our clients, if they have the time, we prefer to send their alternators out to a really good overhaul shop and have them field overhauled rather than to exchange them for a new or rebuilt alternator from Hartzell Engine Technologies. Here's a list of good overhaul shops for alternators that we like to use in various parts of the country, and you can look any of these up on the internet and get their contact information. But if there's time, and it usually takes on the order of a week to get them to turn an alternator around if you send it to them, if you have time to do that, we would prefer to send alternators out to these shops for repair or overhaul rather than to exchange them. Because if they go out to one of these shops, we know that they're going to do a really, really first-rate job of repairing or overhauling the alternator. Some manufacturers and some shops recommend that alternators should be replaced after 500 hours on a prophylactic basis. We don't like to do that. One of the reasons is exactly what I just talked about, that we've seen a very high infant mortality failure rate of new and rebuilt alternators, particularly out of HET. And so if your alternator is working after 500 hours, you got one of the good ones, and we'd prefer you don't mess with it. And we think that this notion of replacing alternators prophylactically after 500 hours is more likely to cause an infant mortality failure than it is to prevent an age-related failure. If your airplane has dual alternators, such as most of the modern all-electric airplanes and probably a lot of the home builds, we recommend just running the alternators to failure or until you overhaul the engine, because if you have dual alternators, losing an alternator in flight is not a safety flight issue. You've got a backup. If your airplane has only one alternator, we recommend running it a lot longer than 500 hours, at least 1,000 hours, or until it starts showing some sign of getting old and giving trouble. If you start seeing any intermittence or whatever, that's probably a good reason to replace or repair the alternator. If you're very cautious and not comfortable with those recommendations, then we would recommend pulling the alternator, sending it out to one of those really good alternator shops for an inspect and repair as necessary, not an overhaul. Overhaul requires them to replace all sorts of stuff, whether it needs it or not. If you send it out for an IRAN, inspect and repair as necessary, that gives them the discretion to inspect the alternator and replace only the things that look like they're worn and leave the rest alone. And if you request an IRAN rather than an overhaul, most alternators will only cost about $200 to have the IRAN done, unless the shop finds some major problem with the alternator. And to that $200, you probably want to add an hour or two of labor for your mechanic to remove and reinstall the alternator. And so that's it, Charlie. And I guess I'm ready to do questions if you have some.
Great, Mike. Pleased to report we have right around 500 people with us tonight, so that's
cool.
Always nice to have a good turnout when you do these things. Greg would like to know, why not go with a 4-phase or more winding? Is it a cost-weight issue, or is it just not as effective, or what?
Well, you know, I've never seen an alternator with more than a 3-phase winding. Obviously, the more phases you have, the more complex the winding is, and the more connections there are to fail, and the more diodes that you need in the rectifier assembly. And so 3 phases seems to get the job done, and seems to you know, produce a low enough ripple that it's not a problem. So I'm not sure that there would be a big advantage in going to more than 3 phases. But frankly, I've just never seen at least an aircraft alternator that had more than a 3-phase winding.
Okay, and Mike would like to know, you know, he's heard that certified aircraft have external regulators and internal for automotive units. He's always wondered why this is. Is it a heat thing, a space thing, or is the FAA going Stone Age on us? In experimental aircraft, do you have a personal opinion about which way to go?
Well, first of all, the FAA is always Stone Age. That's just a fact of life. I'm not sure that there's that there's actually any kind of a certification requirement that requires the regulator to be external. I don't think there is. I think it's simply that aircraft alternators were certified back in the days when regulators were external. The internal regulators on automotive alternators is a relatively recent development that was pioneered by the Japanese car makers, and was made possible simply because the size of the components required for regulators is now so tiny that it can be hidden away easily hidden away inside the alternator. But you've got all of these legacy aircraft that were certified with external regulators, and I suspect it's just a question of that it would cost a lot of money to get STCs for alternators with internal regulators, because it would represent a major change in the design of the electrical system, and so I suspect it would be expensive to get certified. I don't think there's any particularly good reason from a technical standpoint not to use an alternator with an internal regulator, which is something you're certainly perfectly welcome to do on an experimental aircraft. And I think it probably would make lots and lots of sense to use inexpensive automotive components. I mean, you can buy automotive alternators for just a tiny fraction of what aviation alternators cost, and I would think that if you could put 2 of them on your experimental, rather than 2 automotive ones, rather than 1 expensive certified one, you'd be way ahead to having the redundancy and so on.
Okay, and Daniel would like to know, when you pre-flight your plane, other than checking the drive belt, what else should you be looking for related to an alternator?
Well, the main thing on gear-driven alternators is that you want to look for the presence of oil. The alternators, the gear-driven alternators, for example, on Bonanzas and twin Cessnas and other airplanes that have that alternator mounted up front and bolted to the side of the engine, they have a real critical oil seal that is intended to keep engine oil from getting inside the alternator. If engine oil gets inside the alternator, it'll eventually start polluting the brushes and slip rings and cause a failure. And those gear-driven alternators typically have, I guess for lack of a better phrase, I'll call them exhaust pipe. It's a port that the cooling air comes out of, and if you can see that during pre-flight, and depending on what kind of aircraft you have, sometimes you can see it during pre-flight and sometimes you can't. But if you can see it, you want to look and make sure that it's dry and that there's no oil coming out of it. If you see any oil on it, that means that the oil seal at the drive end of the alternator is starting to leak, and you need to pull the alternator and have it repaired, because if oil starts getting in there, it's only a matter of time until the alternator itself fails. Obviously, on a belt-driven alternator, there's no possibility of oil getting into the alternator directly, because it's not bolted to the engine; it's physically separate. And so, on a belt-driven alternator, the main things you're looking for are obviously the condition and the tension on the belt, and also to make sure that the alternator mount itself is secure, and that if you just put your hand on the alternator and wiggle it, you can't move it very much. It's nice. It's supported nice and tightly. I guess that's probably about all you can check during pre-flight.
Okay. Any opinion on plain power alternators?
Yeah, we've had so far we've had real good luck with plain power alternators. They're the first company that have come up with actually new clean sheet design for aviation alternators for a very long time. As I said, most of the alternators in certificated aircraft are originally based on all automotive designs. And generally speaking, we've had real good luck with the plain power units. They have STCs for a very large number of certificated aircraft, and they offer not only STC'd alternators but also STC'd regulators. And we've had, so far, very good luck with them. Another company that's good to know about that specializes in STC'd regulators, they don't build alternators, they only build replacement regulators, is a company called Zeftronics down in Texas. And they have STCs for lots and lots of certificated aircraft regulators. And the Zeftronics regulators are typically newer designs and more robust than the ones that they are STC'd to replace.
Okay, and Bob would like to know, what's Mike's recommendation for tensioning an alternator belt?
Well, I mean, I guess the generic answer is to follow the procedure in the aircraft maintenance manual, but typically the procedure involves applying a certain force to the belt and measuring how far it deflects, and the specs for doing that are invariably in the aircraft maintenance manual.
Okay, and when an engine, John would like to know, when an engine is overhauled, would you also overhaul the alternator?
You are not required to do so, but it's something that's traditionally done. If the alternator has very low time on it at the time you overhaul the engine, you're not required by regulation to overhaul the alternator the way you are, for example, a magnetos, because technically the alternator is not an engine part. It's an airframe part. And so you're not compelled to overhaul it at engine overhaul time. But it's traditional to do it at engine overhaul time. And I would typically do that unless the alternator had been replaced or overhauled, you know, a relatively few number of hours ago at the time you decide to overhaul the engine.
Okay, and another John would like to know if you have any recommendations for overhaul shops in Canada.
I honestly don't know of any accessory shops up in Canada. I just have to plead ignorance on that.
Okay, and let's see. Peter states a concern I hear is bearing failure, and so the recommendation to overhaul at 500 hours. The recommendation to overhaul at 500 hours. Is this a valid concern?
Did he have to mention what kind of aircraft he's flying?
Did not.
Okay. This 500-hour overhaul thing is something that tends to be fairly rampant in the Bonanza community, in the bearing community, the Twin Cessna community. Aircraft that use gear-driven alternators mounted on the front of Continental engines, Prestolite series alternators. And there's an interesting history to this, and I'll go through it very, very rapidly for you, just so you can understand. But it used to be, I mean, the rationale for overhauling these things at 500 hours arose from the fact that these Prestolite alternators used to experience fairly frequent failures of the bearing on the non-drive end of the alternator, on the slip ring end, if you will, of the alternator shaft. And when the bearing fails and seizes, theoretically the hub should disengage and protect the engine. But the hubs that they used to use back up until sometime in the 90s were not elastomeric hubs the way they use today, but were hubs that used a spring that had a habit of occasionally failing to disengage. So if you had a dual failure, in other words, the non-drive end bearing of the alternator is seized and the spring-style hub decided not to disengage, you could trash the engine. And obviously it's a major tragedy when a $1,000 accessory trashes a $40,000 engine. We don't like to see that happen. However, in the mid-90s, two things changed. One is that the problematic bearings in the Prestolite alternators were replaced with a new series, a new style sealed bearing that literally never fails. I don't think I've ever heard of a case of the bearing failed. The old style bearings were so problematic that they actually had an AD against them. You're supposed to inspect them every 50 hours, and you're supposed to relubricate them if necessary. The new bearings are sealed, they're maintenance-free, and as far as I can tell, they never fail. The second change that happened was that the old spring-style hubs were replaced by elastomeric hubs that virtually never failed to disengage. In fact, they have the opposite problem. Occasionally they disengage when there's nothing wrong with the alternator. So between the change in the non-drive end bearing in those alternators and the change in the hubs, the rationale for replacing them at 500 hours went away twice. And so continuing to replace them at 500 hours is something that's done out of pure tradition, but the reason behind it is long gone away. It's been gone for 15 years or more, and so we recommend not doing it, and that's the reason why.
Jim has a question a couple of people have asked, which is, if my plane has a single alternator, is there any way to add a backup alternator, or does it even make any sort of sense?
Absolutely, there's a way to add a backup alternator, and it probably does make a lot of sense. There are really two solutions I can think of. BNC Specialty Products in Newton, Kansas makes those alternators that are backup alternators that are designed to mount on the accessory pad, the same pad that you'd mount a vacuum pump on. Originally they designed those alternators purely for experimental aircraft. Subsequently, they have gotten STCs that apply to most certificated aircraft, and they have very nice kits that allow you to add that. There's a second kind of backup alternator that I've seen that is also STC'd for certificated aircraft, and it's an alternator that isn't driven off the engine at all. It actually mounts on the underside, typically on the underside of a wing, although I guess it could probably mount on the underside of a fuselage, and you pull a knob in the cockpit and it drops out a door and is wind driven, and provides a second charging system source in case of a failure of the primary alternator. So there are at least those two different methods for adding a backup alternator to an existing single alternator system, and both of them are STC'd so that they can be installed on certificated aircraft.
Okay, and Jim would like to know what should be done if an alternator fails in flight.
Well, I mean, hopefully, I almost hate to answer a question like that because it's so dependent on the actual charging system. Hopefully, the POH has a specific alternator failure procedure. In general, the procedure for most aircraft involves turning off the alternator field switch and then cycling it back on. And if the alternator failure was due to some sort of an overvoltage trip out, that normally is what it takes to reset it. If you have a what's it called, the clamp down kind of overvoltage protection, then you need to check and see if the field breaker has popped, and if so, you would cycle the field switch off, reset the breaker, then cycle it back on. If cycling the field switch doesn't bring the alternator back on, then the problem is something more serious than an overvoltage trip out, and you'll want to turn the alternator switch back off and terminate the flight as early as practicable, because you'll be on battery power only. But again, there ought to be the actual procedure for handling an alternator failure varies quite a bit from aircraft to aircraft, depending on the design of the charging system circuit. So you really want to follow the checklist in the POH that describes what to do in the case of an alternator failure. It varies from one aircraft to another.
Okay, and Phil recently had an alternator failure because of oil contamination of the brushes. Piper Comanche, Lycoming alternator in front. I assume the fix is to extend the crankcase breather so it exhausts overboard rather than inside the cowling? Question mark.
Well, it certainly shouldn't exhaust inside the cowling. Every engine should have a breather line that terminates outside the cowling, typically at the rear and down below. But I'm wondering whether he's sure that the oil contamination in the alternator came from the breather, as opposed to, for example, the front crankcase seal. On a Lycoming, typically the alternator is right up front, right below where the crank shaft comes out of the front of the crankcase, and a leaky front seal would, among other things, let oil get into the alternator. So you need to make sure you know where that oil was coming from before you fix the problem. I would certainly hope that the breather is rooted somewhere outside the cowling. You certainly wouldn't want the breather to be expelling oil inside the cowling. But on a Lycoming with a front-mounted belt-driven alternator, I would wonder whether maybe that oil was coming from the front crankshaft seal or something like that.
Okay, and I got to share this one from John. He says, not a question but a comment. What an outstanding presentation, taking the magic out of the alternator and replacing with a clear, simple explanation. Next time a mechanic tries to to fix a charging system problem by saying you need to replace the alternator, I'll have some very intelligent probing questions to ask. So I think that ultimately is the goal of these presentations that you give, Mike, to arm the owner with the information that they need to have those intelligent questions.
Well, those are very kind comments. I appreciate them, and indeed, one of the things that I see a lot in my practice when we're working with hundreds and hundreds of shops and mechanics all over the country, and indeed actually all over the world, is a failure of good troubleshooting procedures, particularly when it comes to electrical things, and a tendency for mechanics to do what we call shotgunning the problem, which is to just start replacing things based on guesswork rather than pulling out a meter and actually figuring out what's wrong. And countless alternators and regulators and other expensive components have been changed unnecessarily because the mechanic was guessing what was wrong rather than actually troubleshooting to figure out what was wrong. And there tends to be a natural tendency, both on the part of mechanics and aircraft owners, that if an alternator ceases to charge the battery, to just assume that the alternator is faulty, when frequently it's not the alternator's fault at all. And as I try to point out in this webinar, troubleshooting a charging system is not rocket science. It's a very simple circuit, and there's a very simple step-by-step checklist that you can go through, which I tried to present several times, to determine what's wrong. And it really is important to make sure that when you take a charging system problem to a mechanic, that you make sure he actually goes through the appropriate troubleshooting steps, as opposed to just assuming that it's the alternator or the regulator that's bad and replacing it on speculation, because frequently it's not any of those. It's a broken wire or a bad connection or something like that. And you can run up a very large bill replacing components that actually weren't the cause of the problem.
Okay, and Nick has a twin Cessna, and he's considering a plain power alternator to get better low RPM amperage. Can I replace just one, or would a mismatch be a concern?
It depends on the twin Cessna, but for most twin Cessnas with paralleling regulator or paralleling alternators, I would be inclined not to replace just one, because I suspect that you will have problems getting dissimilar alternators to parallel properly with one another.
Okay, and Sean would like to know, do you have a recommendation about replacing belts only when you replace alternator, or just as needed?
Well, my general philosophy is to replace stuff only as needed. So I'm real big on inspection, and I'm not very big on prophylactic replacement. I believe we inspect things, and when they start to show signs of wearing out, then we replace them.
Okay, and question here, should I start my IO550B engine with both BAT and alt on, or BAT only on?
That's an interesting discussion, and I won't belabor it, but in general, I'm a believer of starting engines with the alternator switch turned on. And the only time that I would recommend actually two times
Mike,
that I would
Mike, you cut out right when you were concluding what your recommendation was. Could you just start that one over?
I could. Is my audio okay now?
It just cut out right when you said, I recommend, and then it kind of left us.
In general, with two exceptions, which I will get into, I recommend starting the engine with the alternator switch turned on. The two exceptions are, one, if you are starting the alternator on external ground power. If you're starting the engine with when it's plugged into a cart, then I recommend starting with the alternator turned off, and then once the engine starts, turn the alternator on and have them unplug the cart and turn the alternator on. The second exception would be if you're starting the engine with a significantly discharged battery where you're really worried about whether the battery has enough energy left to start the engine. And in that case, starting with the alternator turned off will save you an amp or two of current draw. That is what the field would draw. Except for those two exceptions, a GPU start and start with a depleted battery, my recommendation would be to make all starts with the alternator's switch turned on.
Okay, Craig would like to know your opinion on internal backup batteries such as Garmin and Dynon use instead of having a backup alternator.
Well, I think conceptually the idea of having a built-in backup battery is a good one. On the other hand, the prices of some of these backup batteries, particularly on Garmin devices, is totally outlandish. I mean, they're just ridiculously expensive, and I have a problem with that. But conceptually, I think it's a good idea.
Okay, and just kind of a follow-up to the question about startup is, what about shutdown?
There's no reason to, if the question is there some good reason to shut the alternator down before you shut the engine down, the answer is no.
Okay. And let's see here. We had, let's see. Oh, Rick would like to know, what are typical early failure symptoms of an alternator?
If the alternator is going to give you early failure symptoms, it's typically going to be intermittent. And most of the time that it's intermittent, it means that there's a problem developing with the brushes and slip rings. Or there's some kind of a loose connection developing in the rotor. The other common failure mode, which is a failure of a rectifier diode, is typically non-intermittent. When they fail instantly, and they stay failed. If you have a bad rectifier diode in an alternator, the most common symptom that you'll notice is you'll suddenly notice a whine in your headset that wasn't there before, and it's a whine that will change in frequency with engine RPM, and one that will go away if you turn off the alternator field switch. So if you hear a whine in your headset that varies with RPM and that goes away when you turn off the field switch, you can be guaranteed that you lost a rectifier diode in the alternator, and that the alternator is going to have to get repaired or replaced.
Okay, and Jim would know, what's the cost of a rebuild and the cost of a new alternator?
Well, it varies all over the map depending on the capacity of the alternator. I mean, for example, on my Cessna 310, which is a known ice airplane, I have 200 amp Prestolite alternators, and overhaul exchange cost on those alternators is about $1,000. I wouldn't even hazard a guess what a new one would cost, but it would be more than I would be willing to pay. 50 amp alternators that are commonly found on single engine aircraft are considerably less expensive, more in the $500 or $600 range. As I said, an IRAN, where you send the alternator out to be opened up, inspected, and the worn components only replaced, it will be often on the order of $200. So that should give kind of a general range of prices, I think.
Okay, and Thomas asks, could we get the name of that wind-driven backup alternator again?
Boy, that one escapes my memory right now, Charlie. I'd have to go look it up on the internet, and I suspect it wouldn't be hard to find, but I cannot remember just off the top of my head the name of the company that makes that system.
Okay.
I'm sorry.
No problem, Mike. Also had a question about questions about will this be available either later on, and the answer is yes. We will post this recording to www.eaa eaa.org/webinars. In fact, should be up by tomorrow afternoon. You'll be able to go through the entire presentation. Mike, we're pretty much up against our allotted time right now.
22 after.
Well, that's what I actually say it's going to go to. I have a laundry list of questions here, but for people that want more information, because either their question didn't get asked or they have follow-on questions, what do you want them to do? You want to send them an email? You want them to send you an email, right?
Absolutely. My email address is on the screen right now, hopefully.
Yep. And then the other option.
Questions that didn't get answered, please go ahead and feel free to send me an email. I'll try to answer all the questions.
Okay. Jim chimed in that Basic Aircraft Products makes a wind-driven alternator. I don't know if that's the one that you're thinking of.
Yeah, that name does not ring a bell with me, but it's quite possible. I'd have to research that. I just can't recall.
Okay. The other place that you can go for maintenance information, and I know you monitor these, we do have a forum board, eaforums.org, where we have a maintenance subcategory in there. And Mike, I know you monitor that as well as quite a few of the other people in the EA world.
It's a real good place to go to get maintenance questions answered. There are a number of people in addition to me that monitor that forum, and it's a good place to get answers.
Okay. And somebody wanted to know my email address. It's cbecker@ea.org if you need to contact me for any reason. But Mike, great presentation. Any closing thoughts?
No. There were real good questions tonight, and next month we're going to be doing one on tires, which pretty much applies to everybody. So looking forward to doing that one.
Okay, and somebody else chimed in with GenniPod, GENNIPOD wind alt.
So I guess there are several companies that make those, and we probably have to look to see which ones are limited to experimental aircraft and which ones are STC'd for certificated aircraft.
Okay. Well, Mike, thanks for everything. I want to thank everybody for tuning in. I think we had just over 500 people tonight, so a great turnout. And once again, this webinar will be available at eaa.org/webinars. And if you're not yet an EA member, I would invite you to join. And if you'd like to join, just go to eaa.org/join, and that's where you can sign up. So thanks, everybody, and have a great night.
Good night, everybody.